Hello friends, in the last video we have seen the introduction of oscillation. Now here let us try to learn more about oscillation. Let us discuss. Okay, uh, example of oscillation was taken as simple pendulum there. Okay, let us take some other example. Maybe I have a spring here like this. Okay, and I attach one hook here. Okay, now so far nothing has been attached with this spring. Okay, it is just attached to this rigid support and the spring is free. Okay, now suppose I attach one mass here. Okay, now what happens? Now depending on how stiff the spring is, the spring will the length of spring will increase. Okay, and then again it will remain in some equilibrium position. Okay, now what happens? This mass is m and this weight mg is acting vertically downwards. Now what I'm going to do is um, I'm going to pull this mass down through some distance and just leave it. Okay, now what happens? What do you expect to happen? Now this is a spring, correct? So once I pull the mass down and just leave it, the spring is going to pull the mass upward, correct? And then it will tend to pull it back to this position. But then again, will it stop there? No, the mass will further tend to move up and compress the spring. Now initially the mass was pulled to expand the spring. Now it is going to compress the spring. So anyway, whether it is extension or expansion or compression, the spring is going to resist. Okay, the spring wants to remain in its equilibrium position, correct? And then that will give rise to oscillation, and we have seen this kind of oscillations, right? When we sit in the car, we have shock absorbers, shock absorbers in the car. And what is the function of shock absorbers? Shock absorbers, they have springs there. Okay, so whenever some pothole comes, what happens? The tires, they go in the pothole and the whole thing, it bangs down, and then because of spring, what happens? The shock is absorbed. Okay, so that those shocks are not transferred to our bodies and we feel we get a comfortable ride. Okay, now so that is one example. Here I'm going to take another example here. Now it is going to be something similar to this, but then this spring was vertical spring. Okay, now I'm going to have my spring horizontal. Okay, and use some other one. I have this rigid support here, and this is a fixed surface, right? From this rigid support, I have this spring here, and there is this mass m. Okay, now I'm drawing this mass large enough so that you are able to see it properly. Now this is my normal position or equilibrium position. This surface on which this mass m is resting, that surface is absolutely smooth. Now when I say absolutely smooth, what does it mean? It means that there is no friction, which sounds hypothetical, but then we have to assume and you have to trust me, right? So this surface, I'm saying that it is frictionless. So see, when I say frictionless, what am I doing? I'm eliminating any other unwanted things to interfere in the thing that I'm going to derive here, isn't it? Now what I'm going to do here is I'm going to pull this mass towards right. Okay, now what happens? My second position, again, this is the surface. Now this mass was here, and now here, just look at the spring here. Now the mass is going to move some distance here, correct? Mass m here, and this displacement, let us call it x. Now here one thing we need to note. Okay, suppose you pull the mass through a very small distance. Okay, very small distance. Just try to visualize. Just try to visualize as I'm saying this. Okay, this is my spring, and that mass, my spring is fixed, and the mass is being pulled through a very small distance, and just leave it. What happens? It will, it will start oscillating. Correct. But now pull it little more. Okay, and then it starts oscillating like that. Okay, as you are increasing the displacement, the restoring force which the spring is exerting, is it not greater? Correct. So the restoring force exerted by the spring on the mass, it is proportional to the displacement. Okay, so we have something like this. Okay, my displacement is in this direction, x, and my restoring force, F, is in the opposite direction, and as we rightly visualize, we find that this force is proportional to the displacement. Greater the displacement, greater is the force. Correct. Now when I have proportionality sign here, but I don't want that sign. Okay, I want equal to sign, I want an equation. Okay, so I'll introduce some constant of proportionality here, and then my equation becomes F is equal to K into X. Okay, but now here one thing you would note. Okay, my displacement is in which direction? It is in the right direction, it is towards right, and then my restoring force is towards left. So the direction of force is opposite to that of displacement. Correct. So obviously I have to introduce this negative sign here. Okay, that would indicate that force and displacement are acting in opposite direction. Correct. But then I have to write an expression which is true all the time, isn't it? So let us check what happens next to that. Okay, this force is pulling the mass which is displaced towards right, towards left, and towards left. It wants to come in this position. This is the relaxed position of the spring. Okay, but now when it comes here, and my surface, this surface, okay, over here, it is frictionless, the mass will not stop there. Okay, it will tend to move further. Okay, so in this case my spring was expanded. Now it would look something like this. Okay, my spring is like this. Okay, and then this mass here, and this was my initial position. Okay, and you would find that I had taken the mass x units towards the right. Now it has moved x units towards the left. Okay, now the spring has got compressed. This is the normal position of spring. This is expanded, and this is compressed spring. Correct. So anything which is compressed would tend to push it back. Okay, now here in this case you would see that my displacement is towards left, and my force, restoring force acting, that is going to be towards right. So anyway, the force is in a direction which is opposite to that of displacement, isn't it? So then this expression which I wrote here, that makes sense. Okay, now I have introduced this constant of proportionality, then we need to name it. Correct. So how do we do that? Now so numerically, okay, numerically I would say F is equal to K into X. Correct. So my K would be equal to F upon X. Correct. So it is the ratio of internal elastic restoring force exerted by the spring per unit displacement. Okay, so it is ratio of internal elastic restoring force to displacement in the spring, and this K, this constant K, it is called force constant or spring constant. force constant or spring constant, and its units would be SI units would be Newton per meter. Okay, and one more thing, when I say force constant or spring constant, it would be constant for a given spring. Okay, for different materials, there can be other different constants, but then this spring constant, okay, will be, it will be constant for given spring. There can be two springs made of same material, absolutely same composition of elements in that. Okay, but they might have different spring constants, and the constant, the spring constant, would depend on the material of the spring. It would depend on the geometry of the spring, and and so on. Correct. So that was about this spring mass system. We are going to use the spring mass system in the next video, and over there we will be deriving the differential equation of simple harmonic motion, something called simple harmonic motion, which we will discuss in the coming video. Thank you so much.